of your interview.
Okay. Maybe we should start. Hello, everyone. Good to see you all in person and virtually. Just like previous weeks, when we covered the fundamentals today, you will have the 3 discussion topics starting this afternoon. So remember to submit your first response before Saturday or Sunday, I can't remember, but give Christos a bit of time to read through your responses. Okay, today we're going to talk about the certification, and I'm gonna put emphasis on differences between metals and composites. But first, let's start with simple questions. What are the loads on an aircraft? So 2 definitions, limit load, ultimate load. If you look at all the loads that are applied on a structure, in this case aircraft, I'm going to go over the types of load that we might get. The maximum load that the aircraft would see during its lifetime, we call it limit load, LL. That's how I'm going to show it, limit load. The maximum load, which is a combination of many loads that we're going to go over them in a second, is called limit load. If you take that load multiplied by safety factor, which is 1.5 for an aircraft, it's called ultimate load. And I'm going to talk about the types of loads and the safety factor 1.5 and why 1.5. Actually, one of the discussion topics today is about this 1.5 factor. So I'm going to go over that in more details. So what are the loads on a structure? Some of them the pilot can control, some of them the pilot can't control. So the one that the pilot can control is the flight envelope. Basically, the acceleration, the speed, those types of things are creating drag and thrust and lift and other forces on an aircraft. Those things the pilot can control. That becomes quite important when we talk about the safety of a structure, because sometimes accident happens mid-flight and the pilot can reduce the amount of load on the structure. And they will go through that cases in a bit. But beyond that, there are things that perhaps are accident or outside of the control of the pilot. The engine torque is one thing, but sometimes accident happens and one of the engines is gone. Now it's an asymmetric torque. So the structure should be prepared to handle that extra load. It's a pressurized vessel. When you go to high altitudes, there is built up pressure inside, more than the pressure outside. That is extra load on the structure. So if accident happens, pilot can start reducing the elevations a bit. And then as you go lower altitudes, then the pressure drops and drops and drops, the load becomes less. So if accident happens, pilot can start reducing the altitude, start reducing the flight envelope. And that reduces the pressure, the force on the structure. There is the landing and force that's, of course, is understandable. But there are other things that are, let's say, not quite clear. The upward gust load is quite probabilistic. Sometimes it's a high load, sometimes low load. What do you consider? Do you consider all possible cases in the lifetime of the structure? Do you design for all potential gust loads that the structure might experience? So we're going to talk about probabilistic approach in a bit. There is a fatigue, long-term mechanical loading that reduces the mechanical performance of the structure. There is crash landing load, and you're not designing the structure to drop from, I don't know, like 1,000 feet or what. So it's designed to handle a drop from almost a 3-story building. So that would give us the velocity of around 30 feet per second. And the structure have to be designed to this crash landing force, and you have to show that it can handle that. By handling, I mean the passengers are safe and they can safely exit the aircraft before it collapses. There are impacts, but there's also, it's not quite clear. Bird strike is one thing. We have small birds and really, really large birds. And really large bird can damage the aircraft significantly. What do you consider when you're designing the aircraft? There is ice impact. So some of these you consider, some of them there is a threshold that you stop worrying about the performance of the structure. I'm gonna define those more clearly. Any questions on the type of load? Again, LL is limit load, maximum load that the structure will see. UL is the ultimate load. When you take that limit load, you multiply it by a safety factor, which is 1.5 for our case. So this is what FAA says about the factor of safety. There is this Federal Aviation Regulation FAR 14 CFR, and it says 25.3.03. It says, unless otherwise specified, a factor of safety of 1.5 must be applied to the prescribed limit loads, which are considered external loads on the structure. And then it defines also the ultimate load. It says if you talk about ultimate load, you don't need to consider factor of safety. It's basically a definition of there's an ultimate load, there's a limit load, and factor of safety 1.5, right? Is there anything strange about this slide? Do you see anything strange? Anything weird about this statement? 1970. This has been the rule since 1970s. So in the past 50 years, we have changed the design of the aircrafts for sure. We have changed the material. We went from metallic aircraft to composite aircraft. Why didn't we change 1.5? Stays same as before. Go back a bit. 1934, there was no FAA in 1934. It was Department of Commerce at that time. It says minimum factor of safety is 1.5. And these are the type of aircraft you had in 1938. This is the iconic Boeing 307. That's the shape is so iconic for an aircraft that we actually kept that cigar-shaped type fuselage, and the wings, even though in terms of like aerodynamics is not a perfect shape, but we kept that shape, right? And we had the first all metallic aircraft as well. So it was the sort of era that we started transitioning to all metallic aircraft. But the safety factor has remained 1.5 in the past 90 years. It's never changed, right? You go back a bit further, 1929, and the factor of safety is 2. So somewhere between 1929 and 1934, Department of Commerce changed the factor of safety from 2 to 1.5. And the aircraft design went from this types of design where there were wood components in the aircraft to all metallic. So when we changed the material from wood to metals, we changed the safety factor to 1.5. Why not when we went to composite aircraft? Why didn't we change the 1.5? So that's something to think about, and that's the part of the discussion topic you're gonna address today. But then going back to this, why do you think 1.5? Where does it come from? Actually, going back all the way to Wright's brother, the first aircraft, the safety factor was 5. One of the brothers wrote to his father that I'm designing something that can fly, and I'm going to design it such that it can carry 5 times my weight. So not exactly factor of safety 5 compared to his weight. He was trying to design something that can carry 5 times his weight. But then we came up with 2 at some point for wooden aircraft, let's say, and then to 1.5 for metallic aircraft. Any thoughts where 1.5 comes from? There was no historical evidence back then. They had to choose something. There was nothing, oh, it worked for other aircraft, let's pick something. No, they had to, it has to be based on some thoughts. Yes?
Based on automotive at all?
No. But I'll give you a hint. For factor of safety, 2 things are important. Below limit loads, you don't want to have any deformation, permanent deformation. So aircraft flying, you don't want to have permanent damage all the time. So you want to design it such that it would never experience permanent deformation. And then beyond that, it should never fail. So think about that permanent deformation. Where do you think 1.5 comes from? Yes. At that time, the ratio between the ultimate strength and the yield strength of aluminum was 1.5. So let me do a sketch. So this is stress strain curve of the aluminum at that time. It's not anymore. It has changed, but so that if you load the material in tension, sorry of my drawing, it's not this, but then this elastic, and then it's yielding, and then it's ultimate strength. And this value of the sigma ultimate versus sigma yielding at that time was, the ratio was almost 1.5. It has changed ever since, the material has changed. So this was the idea behind it. If you stay below sigma y during the lifetime of an aircraft, it would never experience permanent deformation, right? So you would design the aircraft to sigma y. There is an additional 1.5 safety factor until the aircraft fails. So the moment they start showing plasticity, you would know that there's something wrong in your design. It went beyond the limit that you designed for. It's like a visual safety factor for them. The moment you see permanent deformation accumulating in the aircraft, you realize that your design was not good. Go back and change it. But you were designed for sigma y, an additional 1.5 safety factor until the aircraft fails, basically breaks under that load. But the metals that we're using have changed, and we changed the material and we kept 1.5. Now why? Why do you keep 1.5? Yes? Yeah, yes, it's a trade-off and it works. Why rock the boat if everything works fine? But then we changed the material, right? So we didn't have experience for the material. So then why? So it works for metals, I agree. So let's say from 1934, we didn't change it all the way to 2000s. But beyond 2000, we started having composite aircrafts. No historical evidence for them. Still 1.5. The reality is that you're going to see, it's, I don't expect you to know the answer of this, but there are hidden safety factors for composites that in reality, they have much more higher safety factors than 1.5, which metals don't have. We're going to go through those hidden safety factors, if you will. We call them knockdown factors, that you reduce the strength of the material or you increase the load, you apply a factor to increase the load during your test or reduce the strength. It's kind of like indirectly helping the 1.5. So we're going to go through that. That's the one big thing. So the results of that is that the composite aircrafts are not optimized for weight because their safety factor is actually a lot more, the actual safety factor is a lot more than 1.5 because of all these factors that we apply. And we're going to go through those factors. Okay. So how do you show that the structure is safe? We call it proof of a structure or substantiation. Two things. It must support limit load without permanent deformation. It must support ultimate load without failure for 3 seconds. So it must be able to handle 1.5 times maximum load the aircraft would ever experience in the lifetime of the aircraft. Multiply that by 1.5 and should carry that load for 3 seconds minimum. And you show that through different methods, but actually at the end of the day, it boils down to two main methods. You do some analysis. So when you want to do show that it can survive crash landing, you make section of the fuselage, you load passengers, dummy passengers, and some cargos, and you drop it from like the 10 meters high elevation, and then it drops, and then it breaks, and it goes through the formations, and you do a simulation, and you kind of show that it's matching the simulation. This is called analysis supported by test. Or you can eliminate analysis, just do tests. So these two are both acceptable by FAA and that have been used. The second discussion topic is for you to discuss advantages, disadvantages of these two methods. I'm going to go a bit in more details why we do analysis supported by testing and why a company might choose testing alone. But imagine that you are in charge of a testing program and your manager asks, this is a small aircraft, testing costs this much, analysis costs this much. Do you suggest me to do both testing and analysis? Or do you suggest me to eliminate analysis, just do more testing? And it's a big decision that someone has to make. It has cost implication at the end of the day. So typically, this is the way we do for large aircrafts using this method, analysis supported by testing. Even though you can do testing alone, but we typically don't do that. Let me walk you through this. I talked about building block pyramid before, that you have to do a lot of tests at the coupon level, a bit less tests at the element level, and you add the complexity of the structure all the way to one large structure, for example, the wing of an aircraft, and you do one test at the end. So at the base of the pyramid, you might do 10,000 tests. And then all the way at the end, you might do just one test. If you want to do it in parallel with analysis, it's something like this. You do some tests. People are in charge of testing. They share results with people who are in charge of simulation. They try to simulate the exact same thing. You go one level up, testing, simulation. You try to simulate what you see and validate it. Go one step higher, one more testing, more analysis. So every time you do testing and analysis is following testing. You do testing first, get data, build analysis, and show that you can predict that. Why? It's so redundant, that process. I mean, you do the test, and the only thing that simulation does is try to predict what happened. I mean, you already know what happened. You did the test. Why would you even go through that process? So that's, yes. If you get different results, that means that your analysis is wrong. But why would you even do analysis in the first place? And that's the real question that a manager might ask you, because they see the costs attached to making those simulations, right? So two things to address. If you don't do analysis, I'm going to talk about that. FAA says you cannot do 100 tests at the structure level. You cannot test 100 aircraft and crash them at different loads. So they make you to do more tests, but they also apply a factor on your design. So you have to increase the loads a bit in your calculation to factor in any unknowns. That increases the weight a bit. So there's a weight penalty if you don't do. But why would FAA cares about that? Still doesn't solve the question. You're doing unnecessary things, apparently. The simulation doesn't add anything here, maybe cost. And if you don't do it, FAA forces you to do more tests. Why? I mean, I can understand why FAA might ask you to do more tests, because it's less confidence, perhaps. But what confidence? Why do you need validated analysis methods? So what you're doing here is that you're validating an analysis method for future applications. Let's say 1 year from now, you slightly change the material. You slightly change your the bonding process. You go from, I don't know, number of bolts to small number of bolts. You change the adhesive you're using. You change your oven that used to make composite. Any change you do, what's going to happen at the structure level? If you don't have simulation tools, you wouldn't know. You have to test it again. So the idea is that the future material and process changes are much simpler. Right? I'll give you one example. When you test, when you test the final structure, you have to show a safety factor of 1.5 for 3 seconds. Boeing did that for Boeing 787. They showed that it certified the structure, fine. Airbus was trying to do the same thing, Airbus A350, and it failed at 1.47, the limit load. So they had extra 0.03 load that they had to go higher up to reach the ultimate load and survive for 3 seconds. They couldn't. And in reality, if you can't satisfy the design, you have to go back to square one, redo the entire thing. That's like 5 years delay, billions of dollars of cost, because you made the mistake somewhere in your design. But since they had validated designs, validated simulation, FAA let them to use their simulation, do some small changes that increase 1.47 to 1.5. It took them 8 months just doing simulation, not repeating any of the tests, and they could satisfy the condition. So it saved them a lot of money at the end of the day. Without this side of the pyramid, there was probably no A350 flying even now. So that helped them to recover. But then let's say you're talking about the very small aircraft. And then you have a choice. Example here. These two aircraft are more or less similar, let's say. There's some distinct differences in their design. But one of them, the manufacturer decided to do analysis supported by testing. One of them, the manufacturer decided to do just tests because they thought this is a fixed design. I'm just going to sell it for 30 years, let's say. I'm not going to change the material manufacturing process. I don't have time to go through the validation by simulation. So skipping all of that, the cost was very different. One of them paid less money at the end, upfront, but the other one has the flexibility of changing the design in the future, which the other one doesn't have. So that's a real difficult choice to make. What is it that we are building? So to do a comparison, analysis supported by tests versus test only. You have two options for certification. Advantages, disadvantages. If you do analysis supported by tests, you have less weight at the end. If you don't do it, there's weight penalty. You have to increase the weight of your structure because you're less confident, let's say, about the design. But then test only is typically cost effective for initial certification. The other one, you have to pay substantially higher costs for initial test program. Much longer, a lot more cost. But then it reduces the risk for full-scale tests, which is quite expensive to do. The example I gave for Airbus A350, and future changes are much easier. So it's a trade-off between these two. And for different cases, you might choose different approaches. And typically for larger structures, larger commercial aviations, we go with this top one. But example I showed you for smaller aircraft, you might go with test-only certification. Okay, any questions? Here on Zoom? You're good? Okay. So the first discussion topic today is on the safety factor 1.5. The second one is on this trade-off. And I'm interested to see how you argue this against Christos, who has been doing this for 40 years. So he has seen different cases that you might choose this or the other one. Okay, so I have to draw this because it's a bit complex. Let's go back. The people who are seeing I have to share my screen, I think. Screen, okay. Okay, my board. Differences between metals and composites. Let's say, why is it green? My son draws on this and changes the colors. Okay, sorry. Okay, so let's say I have a graph. On the x-axis, I have time. And this is lifetime of an aircraft, right? On the y-axis, I have, let's say, the strength of like a component, like a panel. Like let's call it the strength. And then there is a threshold, which is the limit load. This is the limit load. So the strength should be higher than that, of course. If it goes below than that, the structure fails. So let's say the strength at the beginning is quite high. And then you multiply that by 1.5, you get ultimate load. People on Zoom, you can see what I'm drawing, right?
Yeah, we can see it.
Okay, okay. So let's say the strength of the material is initially up there. It has to be up there because you test it. You show that at 1.5 times the maximum load, it doesn't fail. So you start with something higher up. Let's say you have a metallic structure and a composite structure. So metallic structure, the strength is initially high. And then as time goes by, fatigue happens. All right, let's say it's we're talking about the panel with like a small opening in the middle, and you start growing perhaps crack around it, and this crack becomes larger and larger as time goes by. More iterations of the load, the cracks become larger and larger and larger. So the strength of this panel drops. So as time goes by, you start noticing that the strength, if you could test it, the strength would go down and down. And then at some point it becomes sharp and becomes faster. And it drops below the ultimate load. And it's quite a reasonable case. It actually happens. If you have a metallic aircraft, you will start growing cracks because of fatigue. You cannot stop it. It will grow. And then at some point, the strength of the material drops below ultimate load. But it's fine because the load never goes beyond limit load, right? That 1.5 was safety factor. But if you don't do anything, it will start going further and further and much, much faster and becomes quite fast. And at some point, the structure fails. And you don't want that. So what you have to do is to have inspection intervals. Every, let's say 3 months, you do an inspection. You go around critical locations, you measure, let's say, the length of the crack. If the length of the crack is, let's say, I don't know, let's say 0.5 inches, I'm just giving an example. It's an indication from your analysis that the strength is already below the 1.5 safety factor. So you go and you fix those cracks. So the strength goes up. So there's a repair that happens. You catch it in your inspection intervals. And now the strength is again top, and as time goes by, again, it drops, goes up, drops, goes up. So that's how a metallic structure works. How do you know what would be your inspection interval? If you don't do it frequently, let's say I'm doing inspection every 5 years, the crack grows significantly and it fails. If you do it every week, it's quite expensive. You cannot take an aircraft out of service and do an inspection every week. How do we know what would be the proper frequency of inspection? Yes? You kind of know, I'm sure you know. You do fatigue tests. You characterize the fatigue properties of the material, so you know how fast it grows. So you know exactly in 3 months' time, how much maximum would be the length of a crack. In 6 months' time, in 1 year. You wouldn't let the crack to grow significantly such that the structure cannot carry limit load. So you will catch it before that. So you set your frequency such that none of the cracks are large enough to reduce the performance of the structure below the limit load. So that's the mentality behind designing metallic aircraft. It's we're going to go over this the proper terminology, but it's understanding the growth and fatigue, set proper inspection time, repair it, bring it back up, and doing it again and again and again. Right. So that's for a metallic structure. But let's see what happens to a composite. Yes.
Does the time that it takes, I guess, for you repair it and it spikes up again, does that get shorter and shorter? That's kind of what it looks like here, like the intervals are getting.
Oh, right. It was my bad drawing. If you properly repair it, then typically you might overdo it even. So it's probably not. So one of the things that FAA wants, if you have a metallic structure, is to show them what is the repair strategy. So you not only show them the interval of the repair, but also the repair strategy. Both of them must be checked, certified, and then you can have a metallic aircraft flying. So Max, let me get to the fatigue. I'm gonna do a bit of discussion now, but we're gonna have one session talking about fatigue, and we're gonna talk about how people accelerate fatigue tests, because it's a very lengthy process, all of these tests. So this was metal. More questions? Okay. So now let's see how a composite structure works. Let's say it's more or less the same strengths. And composite don't experience fatigue the same way metals experience. They do experience fatigue, but it's extremely slow. So if you look at it, it's just the slope that it goes down is extremely slow, and it doesn't happen in the speed that happens for metal. So fatigue is an issue for composite, but it's not a major issue. But what happens is that once in a while you have impact on composite, like it's a small bird strike impact. I mentioned like there is a maintenance crew, they're walking around, someone is walking over the wing and they drop their toolbox on the wing. It's an impact. It has effect. So what will happen is that the moment you have impact, the strength of the material drops, sometimes significantly. And it might drop below the ultimate load. So FAA says if it drops below ultimate load, you have to find it in the next interval of inspection, repair it, bring it back up again, and then continue. So for composite, drops goes back up, drops goes back up. And sometimes it's a small drop, sometimes it's a big drop, and sometimes even drop below the limit load. So I'm going to talk about those. If it drops below limit load and you are mid-flight, what would you do? So those are real cases that we have to go through. But it's a very different approach then. So the idea that we have, the mentality behind certification, is to understand the nature of impacts, estimate the effects and the strength, come up with a strategy to repair them. And so this is another thing which is on top of what happens to metals. If there is an impact, show that in the lifetime of the structure, there is no crack growing around the impact. That's an extremely severe punishment for composite. So it's basically for metal, we don't have this, but for composite, since we are not sure about the nature of impact happens, there's a bit of crack in the material. You have to show that for a life cycle of the structure, that size of the impact zone doesn't grow. It stays the same size. And it lets you to catch it in the next interval, repair it, and bring the structure back to its full performance. But I'm going to talk about this repair strategy and no crack growth approach for composite. Any questions on the impact of composites and then fatigue in metals? Yeah, this slide kind of now summarizes. You probably can now understand what this slide is trying to show. Let me re-explain this. Yeah, so strength, limit load, and then ultimate load. And then you have a composite structure, impact, the strength drops, and then you have to find and repair it. So that's what happens at an impact. For a metallic structure, you have fatigue growth. So initially the strength is pristine and the strength start dropping, and then you have time to repair it, bring it back up, and you have a pristine structure. Okay. This also I have to explain a bit. The fatigue behavior in metals and composites are extremely different. Let's say you're doing a fatigue test, and on the x-axis is the cycles that you do. And in the y-axis, let's say you are plotting the strengths of the material, but you're not doing it one test, you're doing multiple tests. Let's say you have done 1,000 hours of flight time simulation on the material. So on the mechanical and the hydraulic testing frame, you place the material and they go back and forth, back and forth, back and forth, and you measure the strengths after 1,000 cycles. And you get a value, let's say here. If you repeat that test, you might get a different value, a different value, a different value. So there's a distribution. These curves show the distribution. It basically says, look at this way. Let's say this is the pristine strength equal to 100%. How many hours of flight it takes for a metallic structure strength to drop to 50%? If you do the test, sometimes after 10 to the 3 hours, one of the samples fails. The other samples might fail 10 to the 4 hours, but most of the samples would fail in the middle. let's say somewhere between 1,000 hours and 10,000 hours. So if you have to do a lot of tests, 18 samples, 20 samples, and get an understanding of the distribution of that. So the first line is the lowest 10% of the samples. The middle one is the mean. The top one is the 90 percentile. So the lower one we called B basis before. But if you do the same thing for composites, you can see that the strength doesn't drop as much as it drops for metals. But if I ask you, for example, at what hours of operation, the strength of the material drops to 80%, and you do a test, and one of the samples shows 10 to the 3 hours, the other sample shows 10 to the 5 hours, 10 to the 6 hours. It's a lot more variable, slower, but a lot more variable. And that's a problem because variabilities we don't understand. So we have to include fatigue in composites, not because fatigue is a major issue, it's because we don't understand it the way we understand metals. There's a lot more variability in the material. So the way we kind of compensate for that, in the design, FAA asks you to multiply the loads by what they call load enhancement factor, 1.2, 1.3, whatever that is, and then design the structure. So this is, it works. For metals, you say, okay, the maximum load the structure sees is limit load. I'm gonna design the structure to 1.5 times that. That's for metals. For composite, it says, okay, the maximum load the structure sees is limit load. It has fatigue, but I don't understand it. Increase this by a factor first, which is called load enhancement factor. Then multiply it by 1.5. Then design the structure for that. So you see there is a hidden factor you're applying here for fatigue, and that artificially increases the 1.5 because you don't understand the material. We're going to talk about fatigue a lot more in one of the sessions, but I just wanted to give you like some background. And it's a difficult topic, so we're going to discuss it in more details. For now, from this introduction, any questions? Good. Okay, so I've summarized this here, but this is basically what we discussed now. You have a metallic structure, you have a composite structure. Under a static load, you have to show that the strength at ultimate load is like 1.5 safety factor. The metallic structure can survive that without going through fatigue. If you take it through fatigue, its strength drops. Without taking through fatigue, it can survive 1.5. Composites, you have to show that it can survive 1.5 times with most severe acceptable defect and damage from manufacturing and a lifetime of cyclic load. It can still survive 1.5. So it's a lot more strict approach to design. For fatigue, for metal, as I said, you have to say it grows, set the time to inspect it. What is the strength value? Repair it. For composites, there's accidental damage. It should not grow further. You have to find it and repair it. So the approach is different in terms of the expectation of the material. So even though, so going back to the first question, even though the safety factor of 1.5, there are different ways that we are bringing more confidence in the design. One of them was by multiplying this load by an enhancement factor. Okay, so let's move on to a different topic. For composite, we have 3 levels of loads. We call it an ultimate load, which is 1.5 safety factor. Limit load, which is the maximum load per lifetime of the structure. And then a load that the structure can survive if there's accidents. It can continue flying, land before something catastrophic happens. So there are 3 levels of load. If you have, let's say, an inch crack in the material, let's say, we call that, let's say for the 1 inch, the performance of the structure drops from ultimate to limit. It cannot carry 1.5 times load, only lifetime load. We call that threshold allowable damage limits. Anything smaller than that is fine. You don't need to do anything with that. It doesn't do anything to the structure. Beyond 1 inch, if it goes 1.5 inches, now the strength of the material is such that it cannot carry 1.5 times safety factor. You have to repair it. If you grow it a lot more, let's say 5 inches, and it goes beyond another threshold, which we call critical damage threshold, it cannot survive the limit load as well. So it's a critical condition. That's where the pilot has to reduce the load on the aircraft, safely land it, and then repair it. So there are three values that I introduced here. So you knew ultimate load, limit load. Then there is amount of damage in the material that the performance drops. We call that threshold ADL, allowable damage limit. There is the length of the crack or the size of the damage that the performance of the material further drops. We call that CDT, or critical damage threshold. Okay, so now let's go one by one into these and let's show some examples. What might happen to the structure? So there is a table which I'll go through it one by one. It's just for your reference. So we define 5 categories of damage for composites. Category 1 are when damage and defects are tiny. Example is barely visible impact damage. There is an impact on the structure. If you look at it from the side of the impact, there is a tiny imprint perhaps. We know on the other side, there's probably more damage, but we call it barely visible impact damage because we cannot detect it easily. There are other things that you might have. There might be some manufacturing defects. There might be some environmental degradations. These are all category 1. They don't change the behavior that much, right? But we still have to consider them. So this is one more proper definition. This first one, we call it barely visible impact damage. Second one, now it's more visible impact damage. There's a proper definition I'll give you, but then the last one is clearly visible impact damage, right? So the proper definition of barely visible impact damage is that if someone with naked eyes can see it from a distance of 5 feet or more, in good conditioning, it's barely visible. If you cannot see it beyond 5 feet, we call it barely visible impact damage. You have to get too close to the structure. Typically, it's in the range of if there is a depth of dent is more than 0.05 inches, you can see it from that distance. So if you can't see it, so that every flight, there is a maintenance crew goes around the aircraft, and from the distance of 5 feet, if they can see something, it's a visible impact damage. But if they have to get close to the structure and see a bit of dent, there has been a damage, there has been some impact, but it's what we call category 1, which means that the damage is not too much. For this category 1, the expectation is that you don't need to do anything. The structure should carry 1.5 times safety factor. Other times you have to go all the time, repair the structure, right? So category 1, expectation is that it's gonna reduce the strength of the material a bit, but it doesn't drop it below the safety factor. As a maintenance crew, your job is to say what you see, is it category 1 or not? So it's that person's job to say, this was category beyond 1, we have to do something. If that person doesn't say anything, that means that it's fine. That means that the structure can still carry 1.5 times safety factor. Okay, so this is acceptable damage, acceptable defect in the material. So next time you're in a composite aircraft, know that there's probably cases like this, that there has been damage, lots of micro crack in the material. The backside is cracked completely, but the structure is designed to have these types of defects still carry 1.5 times maximum load. So these are all fine damages. Next category, we call it category 2 damages. Visible impact damage is one of those things. Heat damage is sort of the defect that typically comes under this category if it's not too severe. It's just like mostly surface effects. So when you have heat, you start burning, the material goes through pyrolysis, it reduces its mechanical performance. So it reduces the performance at the end, but depends on how large it is. The small heat damages are considered under this type of category. So what happens if you have, let's say, an impact that you can clearly see? It's like, say, it's larger than the size of a coin. It's clearly visible. Or you have heat damage that you can clearly see in an inspection. You call it category 2. And what's the expectation of category 2? It's going to reduce the strength below 1.5 safety factor, not below maximum load. So you're still safe, but the strength is now below 1.5 safety factor. You have to show that with that damage, the structure can survive limit loads after a lifetime cycle of cycle close. So after the lifetime cycles, with that damage, it's not going to fail. In certification, you have to show that. But then you have to repair it after a while. Not immediately, but maybe you detect it now. In the next repair scenario, a year from now, you have to repair it, right? So you have to repair it. The structure is fine, even with fatigue, even for the lifetime of the structure, but the strength is below 1.5 times safety factor. So if a maintenance crew says it's category 2 damage, it's marked for repair, but you're not going to do probably anything immediately because it can survive the loads later on. Category 3 damage. These are more severe damages, of course. For example, it could be that there is like under the aircraft, there was like where the aircraft was landing, there was a car and that's just like impact. So it's crashed the surface and you can clearly see the fibers are broken, lower fuselage. You might repair this like this one. So you patch it with some more composite, but the patch drops later on. So these are we call category 3 damages. These are clearly obvious. You don't need to get close or to bring a coin and say it was barely visible or not barely visible impact damage. This is a severe damage. So what are the expectations on severe damages like this? Category 3. You have to show that the strength is still such that it can carry the limit load. So the maximum load that the structure you see, you design the aircraft to can carry that load. But this time, without any fatigue. So you're flying, or it has happened, the aircraft flies like a day, 2 days, 3 days until the next inspection cycle. It can still survive that. But if you do it 40 years, and in that 40 years, all of a sudden there's an extremely large load, it might not survive it, right? So if fatigue and large load comes together, the aircraft is not designed for it. But if you put aside fatigue, you have to show that it can carry the maximum load in the life cycle of the structure, which is quite severe if you think about it. These are one of those hidden safety factor I call you. You expect this to reduce the performance of the structure, but the aircraft can fly if nothing happens to the aircraft after this severe damage. But you have to repair it as soon as you can, right? Because you don't have the safety factor, you don't have the fatigue reliability. Category 4 damage. These are the damages such as bird strike. You can see what happens to an aircraft with bird strike. Lighting strike, quite severe lighting strike. Exploding landing gears, tires, other things that might happen. These are the type of damages that the pilot immediately feels that the aircraft, there's something wrong with the aircraft. They are trained to realize that there was something had happened and the damage was quite severe. It's a category 4 damage. Upon this, they will immediately reduce the flight envelope. They will immediately start reducing the altitude and they can safely land the structure and then repair it. So you have to design the structure that even with these defects, it can safely fly, but with a reduced load on the structure, right? Again, this doesn't exist for metals, but you put all of these severe punishment on composite because we don't know what type of impact load comes in, right? So I was working with the DLR, which is German aerospace in Stuttgart. So I had to travel a lot to Stuttgart and they have a setup to test for bird strike. And this was this huge gun that they have that they put frozen chicken inside And they had to come up with the carrier, they called it, that goes around, like a foam that goes around the chicken. And it was so messy. And I asked them once, why do you do frozen? And they said, we did it once non-frozen and no one was willing to clean up the mess afterward. So they were doing it frozen so they can clean it after, but it's also a more severe condition. But anyway, we test this in the lab. They simulate it. They show that it can survive after that. All of these are part of that validation. That's why that validation is so expensive. You have to consider all of these cases for simulation and validation. Any questions on category 4 damage? So I'll go through the categories again one by one, what we have to do. But when category 4 happens, you have to show that there's continued safe flight with a pilot aware of the situation, and they can land it safely, and you can repair it afterward. So that's category 4. And then we have category 5, and then I'll show you some category 5 examples. That something happens to the aircraft, and then you have to draw the line somewhere. And this is that line, that the aircraft is not designed for these types of impacts. God forbid if any of these things happens in mid-flights, there would be an accident. But if it's on the ground, I mean, it has to be repaired because the aircraft cannot fly. One of them is a big bird strike impact. You can kind of see the rest of the leg of the bird, but you can see like the wing is gone basically. So there is, if it happens mid-flight, what's the expectation of the structure? You are not designing the aircraft for that. Some hail impact might do this. Some accidents might do this. So we cannot design the structure for accidents. I mean, the structure becomes so heavy that it cannot fly if you want to consider all of these things. What do you think happened here? Yes. Yes. I think it was, I can't remember where it was. It was they were doing the maintenance on aircraft. They wanted to lift the aircraft, and you kind of see they lift the front or back, and it's kind of created that big cracks in the middle. So we call this category 5 damage. And again, you don't design the aircraft for these, but then the question is that, what is the line? How do you know these are category? Why do we choose category 5? And there is a reason for that. I'll explain that, but it's a bit, let's say, unsettling when you hear why. Where did we draw the line? So I'll explain that in a bit. But any questions for category 5? So no load requirement. You don't need to show that it can survive category 5. It's not part of the design. So this kind of summarizes what you have to do. Category 1 to category 5 for composites. Category 1, the aircraft should survive ultimate load, 1.5 times safety factor with fatigue, lifetime of the structure. Those are like barely visible impact damage. When it becomes visible impact damage, once per lifetime load, repeated service load, but set it such that in the inspection you find it and repair it. Category 3, those are much larger damages, only limit loads without the safety factor, without the cyclic load. Category 4, just doing continuous safe flights and landing without any of the limit load and repeated loads. Category 5, that's failure, fail the structure. Okay, let me go 3 slides forward. I'm going to come back to this about the impact. And that is, how do you set the categories? I'm going to come back to those 4 slides in a second. So there is a deterministic approach, a probabilistic approach. The way this has been set is probabilistic. What do I mean? There was a study done by FAA and some other companies, and they gathered accident reports of all the impact that has happened on a specific aircraft. I think there were 1,600 accidents that they had a report for. They gathered how much load was applied in that impact. You can kind of see the number of accidents and then the impact energy. And as you go to higher impact energy, it becomes a rare occurrence. It doesn't happen that often. If you're at the, let's say, 10 joules impact, it happens quite a lot. So you expect to design the structure for that. But as it becomes rare and rare and more rare, maybe like once in like all the 1600 accidents that they have gathered, I mean, it becomes ridiculous to design the structure for that very rare cases. And that's the idea behind designing aircraft using composites. And this is something like this. Lightning strike happens every hour. There is 10 to the minus 3, or every 1,000 hours of flight, one lightning strike happens to an aircraft. That's almost once per year of the service life of an aircraft. So if the aircraft flies 40 years, 40 times in its lifetime, it will experience the lightning strike. So it's quite common. You design the aircraft for that. Bird strike is quite rare, 10 to the minus 7 per flight hour. So it might happen to an aircraft, but it's not as common as a lightning strike. It might happen every, I don't know, I can't calculate it now, but maybe every 30 years, you have one bird strike, right? You design the aircraft for that as well, even though it's rare. Human errors are 9, 10 to the minus 7. Quite rare, but it happens. So you design the aircraft for that. You draw the line at 10 to the minus 9 per flight hour. If something happens, its probability is less than 10 to the minus 9 per flight hour, you don't design the aircraft for that. And we did the calculation for that. It comes from this. If, let's say, Boeing 787 has 1,000 aircraft. Each aircraft flies 40 years. And every year it flies 1,000 hours. And if you do the calculation, it's the equivalent of accident happens to one of the aircraft during the entire 40 years once. So one time, one of the aircraft out of thousands in the 40 years of the aircraft might experience this type of load. And then you don't design the aircraft for that load. But that means that one of the aircraft might fail because of the load that you haven't designed it for. And you accept that. That's where the line is. That's why I'm saying it's a bit unsettling reason behind why we choose these lines. So we design it such that one aircraft might fail, but beyond that, it's not economical, basically. Okay, questions? Let me go back a couple of slides. Yeah, we have a class that we're going to talk about lightning strike. It's quite interesting, at least for me, from materials perspective, because it's a very, let's say, IP-rich, intellectual property-rich as aspects of the design of an aircraft. How do you design aircraft, composite aircraft for lightning strike? But that's the, I think the last class is going to be dedicated to that. Okay, let me go back. Let me talk about impacts a bit more with considering the material. So barely visible impact damage, visible impact damage. But how do you figure out which one is which? And sometimes it's not clear at all. I'll show you one example. The shape of the impactor affects it. Small bird, large bird, maybe an ice, hail impact. What was the material? What was the thickness of the material? What was the manufacturing process? The size and shape of the damage changes. And what is the structural arrangement? Is it like supported by like boundaries that are holding the material, or can it bounces back and forth under that load? All of this affects how much damage you have, right? So we went through this. When you have low energy impact, medium energy impact, and high energy impact, what do you see on the side that impact has happened? So we look at it from this side, and there has been an impact in the middle. So low energy impact, you will create this pyramid type micro cracks in the material. Maybe you break the back layer a bit. And on this side, again, you barely see anything. So barely visible impact damage means that the energy of the impact was low. Visible impact damage, you might see some dents on this side, but no other clear indication. Under that, you might have larger delamination. You might break more layers, much larger footprints of the impactor. you have to repair this because you can see the dents. So it's visible impact damage. So it means that there is some more severe damage under it. But if the impact load goes higher and higher up, at some point, it can actually go through the material. So that would be very high impact energy. All right. So this is a study that has been done with a material which is called IM78552 from Hexcel company. With a layup, which is, this is how many layers? This is 4 times 4. This is 16 layers. 16 layers of material. You had an impactor, which had a 0.5 inches diameter. And then you had different energy levels. You can see the energy levels, 5 joules, 13 joules, 27 joules. And then you can see, this is the front side. This is the back side of the panel, the same panel. So this is what we call barely visible impact damage. 5 joules doesn't do anything on this side. On the other side, there is a bit of crack, and that's fine. The aircraft is designed for that. We don't need to worry about that. Then we have visible impact damage, and you can see a clear dent, or it's a clear visible impact damage. Energy is now 2.5 times 13 joules. On the back side, there is much larger delamination and splits, and then all the way to 27 joules, which clear penetration into the material and then cracking of the fibers. But sometimes it's not quite clear. Here's one example. You had a 1-inch diameter impactor on the top and then 3 inches diameter impactor here at the bottom. So 1-inch diameter impactor creates a clear dent, creates that you can see in the inspection. The 3-inch diameter impactor doesn't do much on the surface because it bounces back. It spreads the energy on the much larger surface area, but under it, there is a large area that's been affected. How do you categorize the damage? Is it category 1 or is it category 2? If you say it's category 2, you have to repair it immediately or in the next inspection. If you say category 1, it's fine. How do you say which one is which for a sandwich panel? Any guess? If you say 2, it's a cost for the airline. They have to pay for the repair. Would you say 2? Imagine a maintenance crew comes in, you're the expert, says, okay, I found on a sandwich panel something which is the size of less than a quarter, and it's tiny. I don't know if call it category 1 and category 2. And you're in charge of the budget. You have to authorize payments or not payments for the repair. What would you do? And imagine you have an extremely difficult manager that will come after you if you make a mistake. If you read the slide, it's actually written on the slide what you have to do. NDI might be necessary. So if you are not sure, you will ask the maintenance crew to go back and do ultrasound. Ultrasound will show you what has happened under it. Then you can make an informed decision. But it's a cost. Ultrasound is also a cost, but it's much better than doing the repair. That's much more expensive. Okay, good. I think that's so. I have one last thing. I might talk about it at the end, but when you're doing the full scale tests, which let's say you have a wing, you create a support for the wing, and then you apply a load. Let's say the limit load is gonna change the wing shape into something which is, let's say, 1 meter deflection at the end. You lift it to 1.5 meter at the end. And you have to show that it can survive it 3 seconds. So that's during the test, that's the proof of structure. But you do it like this. First, you go to limit loads. You show that nothing's happening to the structure. You first go to 1 meter, go back, you do inspection, everything is fine, no permanent damage. Then you might do some fatigue. And then you're doing the ultimate tests. Oh. You create some barely visible impact damage on purpose. You create some manufacturing defects on purpose in critical location of the structure. and then you do the test. So you do the test with all the potential things that might have happened. So all the barely visible impact damage. So you might, let's say the critical location is here. You apply an impactor here, 5 joules, one here, I don't know, 3 joules or whatever that an analysis shows. And then now you have some damages, intentional damages in the structure. Then you do the test and you have to show that it can go to 1.5 times safety factor without failing. Okay. Good. That's the last thing I wanted to mention today. Any questions? Yes.
So with the 10 to the 9th factor for the most extreme case that you know of, I feel like I've heard that number used in statistical analysis elsewhere, or what counts as
improbable.
Case. Yeah, is that like a common convention?
It could be, but also here the calculation of why they chose it at the end. Yeah. But yeah, there was also some statistical study that let's say if you look at all the impact that's happened in the 1600 cases, what's the occurrence of each of them? So maybe it also has something to do with setting these numbers. Yeah. Okay. Thank you, everyone. Don't forget to go over the discussion topics, and I'll see you next week.